Alrighty, so here we have the experiment for our physics video project number 2. Clearly, you can see we have a person pulling on a rope. This rope is attached to a tree and has a weight in the middle in a bucket. And to get down to the physics of this problem, you see each part of the rope that is attached to the weight has a tension going in a direction opposite of each other in the x direction. These x forces cancel out, and then we have vertical forces that combine, which is why we have a tension y that looks like double each of the tension 1y and tension 2y. This ty is opposite in magnitude to the force of gravity down on this bucket. Alright, on to the experiments. So in this first set, we have a 20-pound dumbbell with a bucket and 2 towels that total to 11 kilograms. I managed to get 17 inches off of the ground, while Matthew got 11 inches. In this next set, after this one, we increased the dumbbell's weight to 30 pounds. With the towels and bucket, that was 15.5 kilograms. I managed to get 12 inches off the ground, and Matthew got a quite respectable 10 inches. Now, let's go to Matthew to listen to some calculations.
Hi there. Yes, I will be explaining some of the calculations that were done here. So you'll see here, I have a few diagrams available. So first is my simple free body diagram of before we started to lift the bucket. Then there's a free body diagram of after we lift the bucket. And then there's a vector, sum of the forces diagram right here. And you'll notice that according to these, and considering the fact that the acceleration was 0 at the start and at the end, you can see that the tension forces, or just the tensions that are being applied, cancel out with each other and the force of gravity, which would mean that they would equal 0 acceleration, because that means the sum of the forces is 0, because the sum of the forces is mass times acceleration. So of course we have some more calculations on this sheet right on the back of it right here. You'll note that we were concerned with work, and you can see that we set work equal to the change in energy as well as to the force times the distance that was traveled. And then this is just simply saying that the initial energy plus the change in the energy is equal to the final energy, which is just the gravitational potential energy, because there's no kinetic energy from movement, and any thermal energy that exists is negligible. So of course I kind of solved down, splitting the forces into separate vectors of themselves. You'll see in the diagram to the right where it's a little bit messy, but I split the tensions because I set my x and y directions to be y parallel with the force of gravity, meaning that the tensions had to be split. And you'll notice that although the horizontal components of the tensions are actually equivalent, as I point out below, the vertical ones are not. So one of them is the tree, what it's applying on the rope and therefore onto the bucket, and the other one is what I am applying onto the rope and therefore the bucket, or what Caleb is applying to the rope and onto the bucket. Based on the videos, you can tell that we are actually applying more force onto the bucket than the tree is. However, the tree is aiding us somewhat, meaning that we are not forced to put in all of the force required to make this work occur. Yeah, and just this is at the bottom was just explaining some of the steps of how you get to the sum of the forces in the y direction and the sum of the forces in the x direction, and how the two tensions would be equal to the force of gravity, which is just mass times gravitational acceleration. You can see here, this is me putting them actually into effect, where the gravitational energy, which is mass times gravity times the change in y, 0 was set to the ground, which means that by inputting some of the numbers we got, found it to be about 47 joules approximately. And then using the calculations we had found earlier to determine that the two tensions were equal to the gravity, we find that the gravity is equal to 110 kilogram meters per second squared, which means that these are what the two tensions are equal to, and we plug that into the work formula that we had above, and we find out that it's about equal to the same thing. Based on a separate video, you can do the same calculations, get the same thing, but you'll also note that this should work every time, since the two formulas would just become mg change delta h or mg dx or whatever, which is the exact same thing, so they should always be equivalent no matter what.
Thank you for listening.